Right. All right. Welcome, folks. My name is Joseph Exoric. I am a director of product management at AWS. I cover a number of our database services, including DynamoDB and ElastiCache. I'm really excited about this talk. Brandon is going to join us from Scopely. And Brandon has been giving talks on behalf of DynamoDB and AWS for almost 10 years now. I found it on YouTube. His original talk was on 2016 on DynamoDB. So of all the customers that I deal with, I love working with Scopely. I love working with Brandon. They are one of the very earliest adopters of DynamoDB, and they're phenomenally deep in the product. I think they make me uneasy about how well I know the product, because I think they know it very well, and they've been pushing the limits. They've been very early adopters of both DynamoDB and serverless, and now Valkey serverless as well. And for one of the most demanding workloads that we see on DynamoDB, which is gaming, because you can go from 100,000 to 1 million to millions of customers in a very short period of time. And that's one of the workloads that we're very proud of, and we're very thankful for Brandon to join us today and share how Scopely has been scaling on DynamoDB and ElastiCache Valkey with Monopoly Go. So welcome, Brandon. Thank you.
All right. Thank you. I need the clicker. Yeah, so I'm Brandon, and I'm here to talk about Monopoly Go. So Monopoly Go is a really big game. We launched it 2 years ago, and it ended up being like 10 times bigger than we thought it would be. It was the #1 game that year by many metrics, and we brought on like millions of users in a very short period of time, and in our daily traffic peaks, we would have over 1 million concurrent users playing the game at any given time. So this presented a pretty big technical challenge. So here's a basic overview of our architecture. So we have a pretty basic old-fashioned monolithic style architecture. We have a Unity client built with C# on the front, and then on the server side we have a .NET application also using C#. So there's a bit of shared code, so having C# on both sides is nice. Also, the way that we chose databases was pretty important. We used the general rule of thumb where if the data scales with the number of users, we tend to put it in Amazon DynamoDB. If the data scales with the number of employees at Scopely, then we'll put it in MySQL, because it's not very big. It's like configuration data and things like that. And for special use cases, we'll use Redis for things like leaderboards and temporary job state, stuff like that. So in this talk, I'm going to cover 3 main points. So reliability at scale. I'll talk a bit about cost management, and then I'll share a story on operational simplicity and why that aspect of doing things is really important for Scopely. So first, reliability. Why DynamoDB? And the main reason is because a lot of the alternatives have problems that DynamoDB doesn't. So not to pick on MySQL, but I'm going to use it as an example of why we don't use MySQL for most things. So MySQL has, Aurora MySQL can only have up to one single host as the writer. So there's an inherent bottleneck there on the write throughput that you could have on the whole database. Also, we constantly run into connection limit issues. So because we're a very large game, we have 1 million concurrent users, we have to run like something as many as 2,000 or more hosts at a time in order to satisfy those load requirements. And each of those hosts has to open up 10 or more connections to MySQL. So when you do the math on that, you easily hit sort of the upper bounds of the connection limits on the server side there. We tried introducing things like MySQL proxy and scaling out reader nodes, and that helps, but it only scales to a point. And then also there are issues with unconstrained queries. So if an engineer naively forgets to put a limit clause on a select star from users, and then puts it into production, that could easily chew up all of the performance capacity of the database and take us down for a while. With Dynamo, it's just really hard to do that on purpose. And then the most important one for me actually is that I never have to do cluster upgrades with Dynamo. With MySQL, at some point, they're going to make me upgrade a major version, and it almost always requires some downtime and some praying and finger crossing. And it's a real big pain, and we'd rather not have to ever do that. So that's why we don't like MySQL, and we prefer Dynamo. So next, Monopoly Go has some like inherent sudden load problems that are sort of native to the game. So I'll explain a bit about how the game works so that you can understand why we have this problem. The game's really simple. If you open the app, there's one button. You just click the button, it rolls some dice, your token moves around on the board, and you collect some rewards. It sounds boring, but it's pretty fun when you add in all of these other time-based events that we call mini-games. Now, these mini-games, they always have like a start and a stop time. So, for example, like it's Saturday at 9 a.m., our race mini-game might start. And when the race mini-game starts, the game suddenly has to do a whole lot more than it used to do. And for example, it has to serve team recommendations because you have to form a team and you have to all get in a car together. And then you have to, when you go around the board, you're now collecting extra points that you can spend on to make your car go faster in the race. So as soon as the event starts, we get this sudden increase in load. So you can see in this chart here, we triple our baseline traffic in a short period, like 5 minutes. And this doesn't actually tell the whole story because we have certain Dynamo tables or other components that go from 0 load to maybe 100,000 read or write units per second in that very same short time frame. So because of this load pattern, using DynamoDB makes it really easy because we can just simply put our tables in an on-demand mode. And then what we can do is call a pre-warm API ahead of time so that that table has enough underlying capacity to handle sort of whatever load we think it could need in our wildest dreams. And then when the load does come, it's able to handle all of that load without throttling. For other components like ElastiCache serverless, there's a mechanism called eCPUs. And what we can do is set a minimum eCPU threshold before the event starts. Once the load spike starts and then the traffic stabilizes again, we'll just remove the minimum and let autoscaling take care of it after that. For EC2 and autoscaling groups, we kind of do the similar thing. We'll just set a minimum on our autoscaling group. We'll add a bunch of servers. When the load spike happens, then we'll remove the autoscaling group minimum, and then it will scale back down or stay the same, depending on the load. Also, for our load balancers, we'll set a capacity reservation. And that sounds like a lot of stuff, and we have to do it for a lot of different events. So we got tired of doing it manually, and we eventually built a system that automates all of those activities. A bit more detail on our Dynamo strategy. So when we create a new Dynamo table for a new feature, we almost always launch it in on-demand mode. And we'll call the pre-warming API ahead of time, because even when you create a table in on-demand mode, it doesn't necessarily have like the underlying capacity to go to 1 million reads and writes per second right away. So Amazon recently introduced a pre-warming API that lets you say, hey, Dynamo, I want to pay this small one-time cost to sort of make sure that you have enough partitions and underlying capacity to handle additional traffic should I need it. So when we do one, we'll call the pre-warm API, then we'll launch the new feature, and we'll look at the traffic. And if within a couple of weeks or a month we observe the traffic pattern, and if it looks stable enough, we may switch it into provision mode to save money. But if it's too spiky, we won't do that. Note that like when we do switch it into provision mode, we also might need to switch it back into on-demand mode when we get one of those sudden load spikes again. And you're allowed to do this about 4 times a day, switch between provision and on-demand. So even though we try really hard to avoid throttling, we don't always get it 100% right. So we do have some extra mitigations to avoid the user impact of throttling if it does happen. So our server client to DynamoDB will retry a few times. However, we like to keep our server API's responses pretty fast. So we will give up pretty quickly on the server. But we will hint down to the client that, hey, this is an intermittent failure, and you're welcome to retry as well. And the client will retry a few times. And if it eventually succeeds, then the user might notice a bit of lag or something, but they won't actually get a crash or an error dialog. All right, let me talk about a bit about cost. So one of the biggest things that we look for when we're trying to optimize for cost is the size of our items in Dynamo. So one thing that people don't always realize is that when you read or write to a Dynamo or to an item in Dynamo, the cost that you pay in read or write units is relative to the size of the document. So if your document's like 100 kilobytes, you're going to pay like 100 write units to change even like one small aspect of that item. And we noticed that some of our biggest cost savings actually came from reducing the size of documents and not actually from reducing API calls or anything like that. One thing that in this chart that I'm showing here is something that we built. Dynamo doesn't have a way to like expose metrics on sort of your average or min or max document sizes within a table. So we built this ourselves. We instrument our Dynamo client, so every time we read or write from a document, we report the document size. And that way we can get sort of an average or a P95 or a max size of our documents. And then we can set alarms on this, so when our documents get too large, we can take a look at it and see what the issue is. Also note that there's a hard limit of 400 kilobytes, so with a couple of these documents on the screen, we're pretty close to hitting a problem. So here's an example of a table that has a cost problem. So this is a friend invitation table. So if you want to be friends in Monopoly Go, you can send somebody an invitation and they can accept it. The way that we do this in the database is, or the way that we used to do this, is that we have one item for each user's friend invitation. So when you send a friend invite to that person, you add that invite to a big JSON blob within that item. So for most users, it's not a big deal because they only receive a handful of invitations, but for some users, they get thousands, and the documents can get quite large. So sending a new invite to that person is now really expensive. So we changed this, and here's our new design. So instead of having one document per user, we have one document per invite. And then when a user wants to read their invitations, they query several items at once. And in this situation, we also added a local secondary index on the date so that we could query the most recent ones first. And then here's the sort of comparison. So in the old way, every time we would write to a document, we'd pay somewhere between 1 and 200 write units, depending on the size of the document. Now in the new way, we pay a fixed 2 write units. In the old way, we'd pay 1 to 50 read units, and in the new way, we'd pay 1 to 2 read units. And some of the savings there comes from only having to query the first page. So when the user opens the app, they don't need to look at like 1,000 invites. They only need to look at the first page or the most recent ones. So that's why we got savings there. Okay, now I'll share a story on operational simplicity and why Scopely really values this aspect. So we're game builders. We don't really want to spend a lot of time doing sort of mundane database maintenance or manually scaling or tweaking things to get the best performance possible. We'd rather have sort of a managed system that takes care of that for us. So earlier I mentioned that we did have some Redis workloads as well for things like leaderboards, temporary job state, large user lists, stuff like that. In order to serve these workloads, we had a Redis cluster that was not managed by AWS. It was something else. It was really difficult to scale without disruption. Every time, once we got to a certain size, whenever we'd add shards or something, we couldn't do it without like having a strong user impact. We'd see timeouts, connection drops, all sorts of problems. So we were kind of afraid of touching it once it got to a certain size. Also, we had to set alarms on our memory. So if we got to like 80% of the capacity of the database, we'd have no choice but to add more capacity. And we didn't like having to do this. We didn't have to like having to get paged on a Saturday when we're about to run out of memory, and we'd have to add nodes and then cause user disruption and explain to everyone why the game was not functioning very well that day. So we were looking for alternatives. And we ultimately settled on ElastiCache serverless, mainly because it auto-scales behind the scenes. It does exactly what we want. It grows and shrinks behind the scenes according to our needs, and it's supposed to do that transparently. Also, one thing to note about ElastiCache is that it has the word cache in the name, but I think it's very misleading. It's perfectly fine for non-cache workloads. However, it doesn't have the same durability guarantees as like a DynamoDB or a MySQL. But our old Redis workload didn't have those guarantees either, so we were totally fine with it. Also, we decided to use Valkey instead of Redis, since it's open source and 20% cheaper, so it's pretty much a no-brainer there. And then here are the results. So we got our auto-scaling, no more getting paged on Saturday. No more responding to memory alarms. And one thing that actually was a bit surprising to us was that it was 61% cheaper after the fact. So we weren't looking for cost savings. We were just looking to save our own time. But finance was always happy with this, nonetheless. And we realized that most of this cost savings came because we had to stay over-provisioned constantly in our old cluster because we were too scared to scale it down for fear of causing sort of user disruptions. And one of the bad things about ElastiCache was that we were early adopters, so we adopted it very early. And during this time period, there were a few minor outages of like 1 to 3 minutes that we noticed. But we worked with AWS, and they managed to fix it behind the scenes, and we haven't seen this issue for months now. And we ended up very happy with the result. So now we're in a much better place now. We're not wasting our time with sort of database tweaking and that sort of thing. And that's the end of my talk. Thank you very much. And